Hey class, this is Adam Ward and I wanted to follow up with you on example 1 from class. This is forces on an inclined plane. You can see the problem statement that's given here, and we're going to start by drawing a free body diagram for the plate that's hinged at the top. And so a few of the forces related to the gate are forces in the x direction and the y direction for the hinge, as well as the weight of the gate itself acting through the centroid of the gate. And we've got the force P pushing back the force that's holding the gate in place, and of course we've got hydrostatic pressure pushing on the gate from the fluid. So we know, since the gate's not moving, the sum of the forces in both the x and the y have to equal 0, as well as the sum of the moments about any point has to equal 0. The gate's not spinning. In this case we don't get any information about the weight force, so we'll assume that the weight of the gate itself is negligible. And in this problem, I'm going to choose to go ahead and sum the moments around the hinge. And the reason I do that is because the moment arm for both of those hinge forces is then 0. They're forces, but they have no distance component from the hinge itself. That zeroes out those forces and simplifies my world. So the sum of the moments then is the force P we're holding the gate in place with, acting at a moment arm of 6 feet away, and the resultant force, and that's acting at the location YR as shown in purple. YR is measured from the water surface along the plane itself. And so in this case the moment arm that we really need is YR minus 10 feet because YR includes that 10 feet of wall that is not part of the gate that we're analyzing. So going ahead and calculating some of the components that we need, resultant force is the equation from class, gamma times the depth to the centroid times A. So I'll go ahead and plug in fluid properties and the depth to the centroid. Notice I'm using trigonometry here because we have distances along the wall, but h is measured vertically up. And so we've got to take the component of that. And you can see in orange where that 13 feet comes from. And then the area of the gate, 6 feet along the plane, 4 feet in and out of the board. I get a resultant force of 16,900 pounds. Where that force is acting, it's acting at the center, a distance from the water surface plus the moment of inertia divided by the centroid times the area. This equation we look up in the textbook, and because we're always adding some moment of inertia, in this case for a rectangle shown in the orange type here, that YR is always going to be lower than YC. So I calculate 13.23 feet for the location where that is acting, so 13.23 feet measured along the incline from the water surface, and YR is always going to be greater than or equal to YC. The case where those two are equal is a flat plane, or a horizontal planar surface. Now, with both of those calculated, we can plug into our sum of the moments equation. And solving that equation, I calculate a force of P of 9,100 pounds. Hopefully this example helps you all. Thank you.